Hi everyone, welcome to the class. A very good evening. So today, this is the fourth class on Fourier transform basics that I'm discussing. So I've been taking a series of lectures on Fourier transform and this is the fourth class. And the third class which I'm supposed to take yesterday, due to some internet glitches, I was unable to take it. So third class I might be taking in some other point of time at some other future point of time. So today I'm in some other point of time and some other future point. Right. So in today what I wanted to discuss is condition for existence, as the name says in YouTube also, condition for existence. So I wanted to discuss the condition for existence of Fourier transform, a very important topic. Condition for existence of Fourier transform. This is what we're going to address in today's class. So we're going to clearly understand for what type of signal Fourier transform exists and it is well defined, and for what type of signals Fourier transform does not exist, and for what type of signals Fourier transform exists but not well defined. So we'll talk about that in detail. Hi Arun, hi Umesh, hi Abhishek Kumar. Welcome to the class. Right. So today we'll be discussing about condition for existence of Fourier transform. Okay. Yeah, hi Zubair. Right. So yesterday I missed taking the class because of internet problem. So I'll be compensating that class maybe in some other day. And tomorrow I'm taking a 2-hour session on Fourier transform properties, and we'll be doing problems based on properties of Fourier transform. So we're going to have some really interesting discussion in tomorrow's class. The timing of the class is 8 p.m. 8 to 10 p.m. I'm going to take continuous 2-hour session, but this is not on YouTube. Tomorrow class, that is not on YouTube. Tomorrow and day after tomorrow, which means 28 and 29. Same timing, 8 to 10 p.m. So I'll be taking 2-hour sessions tomorrow and day after tomorrow. Okay. Today also, if possible, and if you are interested, I'll be taking a 2-hour session today also. So after 1 hour of discussion, you tell me if you are interested to get extended or not. Okay. So these classes, the classes that I'm going to take tomorrow and day after tomorrow, those classes are on Unacademy platform. They are also free classes. Everybody can attend. No need of taking any subscription and all that. But you have to attend on Unacademy platform. So maybe if you are through internet, if you are connecting through browser, you can connect, or else if you're accessing through mobile phone, you have to download Unacademy app and then you have to watch the lectures. Okay. So and I'll be providing the links. I think everybody knows how to access Unacademy app, right? Are you aware of it or not? If you're not aware of it, what I'll do is at the end of the session, I'll be sharing my I'll be sharing my contact details. So this is my Telegram group. In this Telegram group, I'll be sharing the link of the class for tomorrow and day after tomorrow also. Whenever I'm taking a special class, I'll be sharing the link in this group. Okay. So if you want the direct link, so you just you can access it from this group. Okay. Or else if you know how to access special classes from an academic platform, that is very well. Okay. If you're confused, you can. This is my personal Telegram ID. You can ping me on this. I'll help you with the link. Girish, no, it's not for mechanical students. Basically, this Fourier transform topic is part of mathematics also, but here I'm trying to discuss from ECE students' point of view. Okay, this will help you, but this is not means whatever discussion I'm going to do. It will be more detailed than what we discuss in mathematics. Okay, preferably ECE. This is more suitable for ECE students. Okay. Fine then. So let us continue then. So condition for existence of Fourier transform. Before talking about condition for existence of Fourier transform, first let me quickly write the Fourier transform formula. X of omega is equal to integration from minus infinity to plus infinity x of t into e to the power of minus j omega t dt. So this is the Fourier transform formula, and I'll tell you the philosophy behind what the condition for existence and all that. Okay, if you're already having Unacademy app, then you can easily access the lectures. Fine. So try to understand it carefully. So whatever I'm gonna tell you now, the point, very simple point, but very powerful point. So the same point you can apply for any other transform also. So whatever transform you're talking about, you want the transform to be always finite. We expect the transform to take only finite values. Finite values means anything other than infinite, we call it as finite. Anything other than plus infinity or minus infinity, we call them as finite values. So whatever transform we take, that transform, we want it to take finite values. We never want this function, we never want the transform, whether it is Fourier transform or Laplace transform or Z transform, any transform, same basic. And the basic is the transform, we expect the transform not to take infinite values. Okay. So transform is expected to take only finite values, Transform is like some function. Once you find the transform, you'll get some function, right? And that function is expected to take only finite values. The values this function will take, they should be only finite values. For the transform to be well defined. Understand this point carefully. So I just said transform, I did not say specifically Fourier transform or Laplace transform or other transform. For all transform, this is the philosophy using which we'll derive the condition for existence. Okay, right. So what is the meaning of well defined? Well defined means no plus or minus infinity values, we can call it as well defined. We can call the transform to be well defined if it is taking only finite values. Finite values means no plus or minus infinity only, no. It's a simple statement. Are you following this statement? Did you understand this statement? If there is any confusion, let me know. Okay, so right. So what are we wanting? So we want, if you want to talking about condition for existence of Fourier transform or Fourier transform to be well defined, if you want the Fourier transform to be well defined or any transform to be well defined, what should happen? That transform should not take either plus or minus infinity values. One of these values should not be taken by the Fourier transform, which means, can I write it like this? X of omega less than infinity. What does it mean? X of omega less than infinity means it is not taking infinity, but it is taking all the remaining values. So if I write like the condition like this, it means it is taking minus infinity. No, I don't want minus infinity also. So can you tell me the modification for this condition? Can I put modulus? If I put modulus, I'm talking about minus infinity values also. So if you apply modulus to minus infinity, you're talking about plus infinity. So modulus of the Fourier transform, if you are talking about modulus of the Fourier transform to be taking less than infinity values, which means x of omega is taking only finite values, not real. Okay, x of omega need not be real. There is no need for the Fourier transform to be real. Mod x of omega, if it is a finite value, which means if it takes some 1, 2, 3, 4 or 2 plus 3j, 5 plus 6j, some finite real part, finite imaginary part. Okay, yes, or else we can also write it as, yes, wonderful. That way also we can write to mesh minus infinity less than x of omega less than infinity. But if you're talking about complex Fourier transform, so Fourier transform can be complex also, right? See this one, x of t, even if x of t is real, this e power j omega t is complex. Because of this complex signal, the result might be complex. The result might be real also. The result might be complex also. We cannot say that. We cannot 100% say that this will be real only. It might be real sometimes. Generally it will be complex because this is, we are getting this Fourier transform by using a formula which is involving complex signals. Okay, this way also, this way of telling is also fine. But if a Fourier transform is complex, then which is more sensible condition? This condition is more sensible or this condition is more sensible? If Fourier transform is complex, you cannot say that it is between two real values. No, infinity and minus infinity are also real values, right? So you're not talking about j part here. So that's why it's better to talk about modulus value than this value. So this is a more appropriate condition to say. If mod x of omega is not taking plus or minus infinity, if it is not taking infinity, it means x of omega is not taking infinity or minus infinity either in real part or in imaginary part. Okay, so this whatever statement I told you here, the same statement I'm trying to represent here for particularly Fourier transform. Zubair, no, actually, I don't teach engineering mathematics. There are excellent teachers for engineering mathematics on Unacademy platform also. You can follow Uma Maheshwar sir. He is excellent for mathematics, and there are some other good teachers also. Okay, yeah. So any transform, same basic. So particularly for Fourier transform also, we are using the same basics. Transform is expected to take only finite values if you want the transform to be well defined. Well defined means what? Not say plus or minus infinity means what? They are undefined values. Whenever anybody says undefined values, yes, they are talking about plus or minus infinity. Okay, well defined means it's not undefined. It's not undefined. Okay, well defined means it's like any other number other than plus or minus infinity. Any other numbers we can call them as well defined numbers. 2, well defined. 3, properly defined. Infinity means what is the value of infinity? We don't know. It is so big that there is no value to define it. So that's why we are calling it as undefined value. Okay, right. So this statement I'm just trying to represent in this format. So you want the modulus of this one to be a finite value. Wonderful. Finite means don't say that, sir, 1 crore is very big. So 1 crore is an infinite value? No. 1 crore is finite. 1 lakh crores is also finite. 1000 crores is also finite. They are big values, but they are properly defined. No. Okay, so 1 followed by 100 zeros, such a big number, but still it is not infinity, it is finite only. Okay, because that is properly defined. No, 1 followed by 100 zeros, properly defined, it's well defined. No? What is infinity? Infinity is so big that you don't know what exact value it takes. We know that it takes very big value, but we don't know what value it takes, so that's why it's not properly defined. Okay, yeah. So Sindhuja, I don't teach mathematics in particular. Yeah, Umesh, we can say that countable values are all finite values. We can say that. Okay. So I don't teach mathematics. Okay, but this Fourier transform topic is part of signals and systems. Signals and systems is a subject which is there for ECE students as well as electrical students and instrumentation students. ECE, EEE, and instrumentation. For all these 3 branches, signals and systems is a common subject and a very important subject. As part of that subject, we have all these topics: Fourier transform, Fourier series, Laplace transform, Z transform, DTFT, a lot more topics. Okay, so I'll be discussing this Fourier transform topic from signals and systems perspective, which will be like more detailed than what you will be understanding in mathematics. So Fourier transform has 2 advantages. One, it is part of mathematics and it is part of signals and systems also. So there is more chance of questions being asked from this topic, because this is part of 2 different subjects. Okay, but concept is same whether you discuss from mathematics point of view or a signals point of view. The concept is same, concept is not different. But the thing is, in signals, from signals perspective, we'll discuss in more detail. So it will be more conceptual than what we talk about in mathematics. Okay, right. Now let us understand this one. So we want this to be less than infinity. So if you want this to be less than infinity, modulus of this to be less than infinity, how should be x of t value? How should be x of t value? So if you want mod x of omega to be finite, how should be x of t value? That is what we want to figure out. So if you can figure out for what condition on x of t mod x of omega will be finite, or for what condition on x of t Fourier transform will take finite values, that is the condition for existence of Fourier transform, or that is the condition for well-defined Fourier transform. I hope you're following. If you want this to be well-defined, there should be some condition that should be satisfied by x of t, right? That condition on x of t is what we call as condition for existence of Fourier transform. Okay, right. Next, so let us understand, let me talk about something. I'm talking about this result, okay? So I'll give you one more result. Tell me which of these two, limits from minus infinity to plus infinity. I'm just giving you two different equations, the first one and the second one. Which among these two is greater? 2 is greater than 1 or 1 is greater than 2? Can anyone observe and tell me quickly? Can anyone observe and tell me quickly? Sindhuja, you can follow Uma sir, Uma Maheshwar sir. For mathematics, you can follow this teacher. He is very, very good. He is available on Unacademy platform, and he'll be taking a lot of special classes also on YouTube and Unacademy platform. You can attend the free classes also initially. Yes, he teaches in English only. Okay, yeah. So wonderful. So I believe all of you have observed correctly. Yes, 2 definitely makes sense that 2 is definitely greater than or equal to the first part. Correct? Yes, Koch's principle. I don't want to name it so in particular, but our common sense says that, right? Whatever is the name of this principle, our common sense says it or not. So if you take some signal, take modulus, take the second signal, take modulus, and then if you integrate, the value will be more, right? Instead, if you are multiplying the signals, sometimes signal will be positive, sometimes signal will be negative. So if both the signals are always positive, if you take modulus, they will be always positive. Positive into positive will be positive. Integration of positive signal will be giving us a bigger value. Whereas when you are multiplying two signals without modulus, what happens? Sometimes it will be positive, sometimes this will be negative. When you multiply, you are trying to find the area of some positive areas, some negative areas together. You might not be getting a very big value. And after that, you are applying modulus. So our common sense says that second part definitely is more than the first part. Okay, right. So yes, and if you know what is Koch's principle, yes, you can use that also. That is also fine. Okay, whichever way, we know the principle, right? Now let us apply this one. Shall we apply this basic now? Let us apply this basic now. So you want the magnitude of Fourier transform to be less than infinity. Let us substitute the formula for magnitude of Fourier transform. Formula for Fourier transform is integration from minus infinity to plus infinity x of t into e power minus j omega t dt modulus. You want it to be less than infinity. You want this to be less than infinity. So by using this principle, so if you multiply two signals and then integrate and then take modulus, this value is always less than this value. Okay, if you want this value to be less than infinity, if you want this value to be less than infinity, obviously you want this value also to be less than infinity, right? If this is less than infinity, because this is bigger than this, the second part is bigger than the first part. No, always second part is equal to first part or greater than first part. Always this condition will be satisfied. Since 2 is always greater than or equal to 1, if this is less than infinity, if this is smaller than, if this is finite value, because this is smaller than this, because 1 is smaller than 2, if this 2 is finite, 1 also will be finite, right? I hope you're following. If 2 is finite, if 2 is finite, Because 1 is always less than 2. If 2 is finite, definitely 1 also is finite, right? Can we say that? I hope you understood this part. Fine. So I'm going back. So if there is any confusion, just let me know. Right. So here, this is like the first part. This is like the first part. You want the first part to be less than infinity. See this one? You want the first part, x1 of t into x2 of t. In place of x1 of t, we are having x of t. In place of x2 of t, we are having e power minus j omega t. So this is like the first part in this equation. You want the first part to be less than infinity. If you want the first part to be less than infinity, which means first part you want it to be finite, the first part will be finite if the second part is finite. No? Okay, if second part is finite, obviously first part will be finite. So they're asking us to make sure that the first part is finite. So let us rewrite this equation. If you want this to be finite, that will happen if the second part, which is modulus of x of t into modulus of e power minus j omega t dt is less than infinity. Correct? This is like first part of the equation, Cauchy's principle we have talked about, and this is like second part. If you want the first part to be finite, if the second part is finite, definitely first part also will be finite, right? Okay, I hope you are following. So from this equation, can I write this equation or not? If you want this to be finite value, if this is finite, definitely this will also be finite, right? According to Cauchy's principle. Is that okay or not? So how about modulus of e power minus j omega t? Whenever there is e power j factor in the power, the magnitude will be always 1. Correct or not? If you want, you can just write it. Cos omega t minus j sine omega t. It's like a complex number. So what is the magnitude of the complex number? Root of cos square plus sine square, which will be always equal to 1. Right? So can we rewrite this one? Can we rewrite this one? It is integration from minus infinity to plus infinity. Modulus of x of t into modulus of e power minus j omega t is 1. dt should be finite. Observe this one carefully. If this condition is satisfied, this condition will be satisfied, which means this condition will be satisfied, which means Fourier transform will be finite. If this condition on x of t is satisfied, then Fourier transform will be finite. Fourier transform is finite means Fourier transform is well defined. I hope you're following. Always we want the transform to be finite only. We want the transform to be finite, which means it should not take infinity or minus infinity values. If you want that to happen, how should be x of t? X of t should be satisfying this condition. Integration, modulus of x of t dt, limits from minus infinity to plus infinity should be finite, which means less than infinity. The value, if you are talking about a finite value, we can also write that as it is less than infinity. We can also write it this way. Okay, so we also call this condition, the same condition, this total condition, we also call it as x of t is absolutely integrable. This is another name for this condition. X of t is absolutely integrable. Just observe the condition, you'll understand why we are naming it as absolutely integrable condition. We are saying absolute because we are taking modulus here. Integrable means if you find integration, it should be finite value. Integrable means if you integrate, if it is resulting in a finite value, we call it as integrable. Absolutely integrable means take the absolute value of the signal and then integrate. If that result of integration, if that result of absolute values integration results in a finite value, we say that the signal x of t is absolutely integrable. Okay, I hope you're following. Right. Any confusions? Just let me know. So let me just make it clear. What is the difference between integrability and absolute integrability? If x of t is integrable, what does it mean? What is the meaning of this? If I say x of t is an integrable signal, what does it mean? It means if you find the area of the signal, just area of the signal as it is, it will result in a finite value. If you find the area of the signal and if it results in a finite value always we write it as less than infinity. If you find the area of the signal and if it is resulting in a finite value, then we say that the signal is integrable. Similarly, but basically we are not interested in integrability, we are interested in absolute integrability. If x of t is absolutely integrable, whenever somebody says a signal is absolutely integrable, then the meaning is if you take the modulus of the signal, which means absolute value of the signal, and then integrate it, if it is less than infinity, if it is finite, absolute integration value of the signal is finite, then we say that the signal is absolutely integrable signal. This is one of the most important points in the signals and systems subject. This point we will be repeating in LTI systems. When you're talking about stability of LTI systems, impulse response of a system, if the impulse response of a system is absolutely integrable, we say that it is a stable system. Okay, in Laplace transform also, if a signal is absolutely integrable, then we can say something about the ROC. And what is that? ROC includes j omega axis. So this condition is a very powerful condition. If a signal is absolutely integrable, we can say a lot of things. We can comment about the existence of Fourier transform, well-defined Fourier transform. We can comment about ROC of Laplace transform. We can comment about stability of a system. Lot of things we can comment. Does converse holds true? Yes. If the signal is satisfying this condition, yes, we say that the signal is absolutely integrable. Or if the signal is absolutely integrable, we say that it is satisfying this condition. Okay. So these two are one and the same. Absolute integrability means this condition. This condition means absolutely integrable. They are not like two different statements. It's not like if you from this you are getting this or from this you are getting this. Both are same. It's absolute integrable statement in the format of a mathematical equation. This is the equation. Okay. Right. So this absolute integrability condition is very, very, very important condition. So just try to understand it carefully. Fine. So what did we learn here? What did we learn here? Let me write it. If a signal x of t is absolutely integrable, that we cannot say, Umesh. Okay, you're talking about these two statements, right? So you're talking about the first and second statements. That we cannot say, right? That we cannot say. Converse, yeah, converse need not be true. If the signal is integrable, if a signal is absolutely integrable, definitely it will be integrable. So 2 implies 1, but 1 need not necessarily imply 2. Most of the cases it will imply, but there might be some cases where it might fail. This need not happen. It will happen most of the cases, 99% of the cases. 2 implies 1 means 1 implies 2 also will happen, but there might be some examples where it need not happen. We cannot 100% say this. But if 2 is happening, if absolute integrability is happening, then definitely integrability condition also will be satisfied. Because, see, if you are taking absolute value, which means negative areas are also becoming positive. So it means you are adding negative areas also, you are making them positive and you are adding. Okay, if you are adding the negative areas also making positive, if you are adding it, if that itself is finite, then if you are talking about integrability, you are not taking modulus, which means negative areas you are adding to positive areas, the value will decrease further. If this is satisfied, or if 2 is satisfied, definitely 1 also will be satisfied. But if 1 is satisfied, we cannot guarantee that 2 will be satisfied. If 1 is satisfied, that does not mean that 2 will be satisfied. We cannot say about that. Okay. Right. Simple example, cos and sine signals, take them. Are they integrable or not? Cos and sine signals, are they integrable or not? See, positive cycles, negative cycles. If you find the area from any point to any point, it will result in a finite value only, no? It will never result in infinite value. Correct? Cos and sine signals have positive cycles, negative cycles, positive and negative cycles. If you find the area from any point to any point, The area might result in 0 or some other value, but finite value. Because we are having positive and negative cycles which might cancel the areas each other. But when you are talking about absolute integrability for cos and sine signals, if you are taking absolute value of the signals, all the negative cycles also will become positive. So all cycles will become positive once you take modulus. And how many such cycles are there in cos and sine signals? Infinite cycles are there. Each cycle has a finite area, let's say. Finite area, how many times we are having? Infinite times we are having. So cos and sine signals, they are not absolutely integrable, but they are integrable. Okay, they are integrable but not absolutely integrable. So simple example of 1 does not imply 2 is cos and sine signals. But many other signals might be satisfying. But there are cases where it might fail. If signal is integrable, does not mean absolutely integrable. But if a signal is absolutely integrable, definitely it should be integrable also. Right. Now let me make the statement here. If a signal x of t is absolutely integrable, then what can we say? Why did we get this absolute integrability condition? We want the Fourier transform or transform to be well defined. Well defined means it should not take infinity or plus or minus infinite values. You don't want this to happen. If you don't want that to happen, what is the condition to be satisfied? Absolute integrability is the condition that should be satisfied by the signal. Okay, that is where we have started the discussion. So whatever discussion we have done, so that is what we are writing it as a statement. If a signal x of t is absolutely integrable, then what can we say? Then Fourier transform of the signal, Fourier transform of the signal x of t is well defined. Yeah. So let me be more particular. Then Fourier transform of the signal x of t exists and well defined. Both exists and well defined. This is the most important part. So this is the condition for well-defined Fourier transform. What is the condition for well-defined Fourier transform? Absolute integrability condition. Absolute integrability itself is the condition for well-defined Fourier transform. Okay, right. So I'll give you some examples to make you understand. So I'll give you some signals. Just comment quickly whether they are absolutely integrable or not. Is that okay? I'll just quickly give you some signals. U of t. Can you comment if this is absolutely integrable or not? Del of t. You can comment about these signals. First signal, is this absolutely integrable or not? Is this absolutely integrable or not? Find the area of it. Absolute integrability means find the magnitude of it, which means if there is a negative part, make it positive, and then find the area. What is the area of this one? So width is infinity, right? For u of t, width is infinity, and height is 1 unit, right? So width is infinity. Infinity into 1 is the area of this, which is infinity. So the area of this is infinity. If the area is infinity, definitely it is not absolutely integrable. It's not absolutely integrable. AI means absolutely integrable. It's not absolutely integrable. How about del of t? So find the value. No? If you are confused, just find the modulus of this and find the area of it. So modulus of del of t is del of t only. Integration of del of t, we know that it is equal to 1. But here it's not, yeah. Since I've given only del of t, the area should be 1. If you want the area to be A, it should be A times del of t. Even if it is A into del of t also, area will be A units. But it is finite only. No? It is less than infinite. Right? So that's why del of t is absolutely integrable signal. Del of t is absolutely integrable signal. Next. How about this signal? This signal. What is its area? Absolutely integrable signal. Simply asking to find the area. When they're saying absolute, if there is negative amplitudes, make it positive and then find the area. So it is completely positive, no? So there is no need to apply modulus also. Find the area, it is 400 units. 400 units means finite only, no? Anything less than infinity, it is finite. Anything other than infinity, we can say it is finite, right? So this signal is definitely absolutely integrable. Okay, so how about R of t? So we know the area of this one, if you look at it as a big triangle, half into base is how much? Infinity, into height is also infinity, half into infinity into infinity. That is the area of this one, which is infinite. So this is not absolutely integrable. The area of this is not finite, this is infinite. Right? How about exponential signal? This signal, what is the area of this signal? You can find the area, no? Integration from minus infinity to plus infinity. If there is any confusion, just find the area by simple integration. That's it. Modulus dt. That is equal to integration. U of t equation is 1. Equation is 1 for the limits from t running from 0 to infinity. The equation of u of t is 1 from 0 to infinity, and its equation from minus infinity to 0 limits, this equation is 0. So that's why I'm removing the limits minus infinity to 0, because in that limits of time, the equation of u of t is 0. And if you integrate it, it is e power minus at divided by minus a. Limits from 0 to infinity, if you substitute, 1 divided by minus a. And if you substitute infinity here, e power minus infinity is 0 minus, if you substitute 0 here, e power 0 is 1 unit, which is equal to 1 by a. Okay, fine. So the area turns out to be finite. If it is an exponentially decreasing signal, correct? Area is finite, assuming it is an exponentially decreasing signal. So this is absolutely integrable. Now let me ask you a question. Observe carefully and tell me the answer. E power 4t into u of t. How about this one? Is this absolutely integrable or not? E power 4t into u of t. If you plot it, it will be looking like this, exponentially increasing signal. It will be like this, exponentially increasing signal. By looking at the equation, you should be able to plot it in your mind. Or by looking at the graph, you should be able to tell the equation. You should be comfortable in converting from one format to another format. So this is how e power 4t into u of t looks like. If you are not able to imagine directly, just observe it. U of t means it exists only for positive time. So if you put t equal to 0, it is 1. Okay. As t increases, the value increases. At t equal to infinity, it becomes infinity. That way you can imagine the signal. And this is not absolutely integrable signal because it is a exponentially increasing signal. Okay, wonderful. Now let me ask you one more question. How about e power minus 4t and e power 3t? First answer this one. First plot the signal, then only you can understand it. Is it absolutely integrable or not? First plot it before commenting. First plot it and then tell me. If once you plot it, you will be able to understand it correctly. E power minus 4t. Is this existing for positive or negative time? There is no u of t here. There is no u of minus t here, which means it exists. It is existing for all time. This is existing for positive time as well as negative time. So let us plot the signal. It's very easy to plot the signal. At t equal to 0, what is the value? At t equal to 0, it is e power 0, which is 1. And for positive time, if time is positive, if t is positive, as t increases, power decreases, no? Or magnitude of the power increases, but power is minus sign is there. So for t equal to 1, it is e power minus 4. For t equal to 2, it is e power minus 8. For t equal to 3, it is e power minus 12. See this one? The value is decreasing or not? The value is decreasing, right? The value is decreasing exponentially for positive time. For negative time, if you observe, as you go from 0 to minus infinity, what happens? Put minus 1, it becomes e power 4. Minus 2, it becomes e power. If we put t equal to minus 2, it becomes e power 8. As you go from 0 to minus infinity, what is happening to the value? It is exponentially increasing. And at t equal to minus infinity, it becomes e power plus infinity, which is infinity. I did not put u of t here. That is the only difference. I just want you to understand that. So this is not, you cannot say that it is simply only exponentially increasing or decreasing signal, okay? Overall, it is decreasing only, but what is the amplitude of this one at minus infinity? At minus infinity, it is having infinite amplitude. So the area in this negative region, for negative time, the area is infinity. For positive time, area is finite. Overall area is infinite. So that's why this signal is not absolutely integrable. Is that okay? This is not absolutely integrable. Similarly, one more example I'll ask you. How about e power 3t? How about this? Plot it and see. E power 3t, how does it look like? As a function of t, if you put t equal to 0, it becomes 1. As t increases from 0 to infinity, the value exponentially increases like this. At t equal to infinity, it is e power infinity, which is infinity. And similarly, as t goes from 0 to minus infinity, the power decreases and it goes to 0 like this. It's exponentially increasing kind of signal, but the area is infinite for positive time and area is finite for negative time. Overall area is infinite. So that's why this is not absolutely integrable. Okay, very easy to guess the signal is whether the signal is absolutely integrable or not. Very simple. You just need to find the area. That's it. Okay. Right. How about the one more question I'll ask you? E power j 4t. How about this one? The power j is there. E power j 4t. Anyone? E power j 4t. J is there in the power. So I'm just asking you whether it is absolutely integrable or not. If you are confused, just apply the condition. No? Minus infinity to plus infinity, modulus of e power j 4t. That's it, right? See here, we are confused here. So that's why whenever you are confused, just apply the condition blindly. Just integrate it. What did we get? Integration from minus infinity to plus infinity. Modulus of e power j value is 1 dt. Substitute the limits. It becomes infinity minus of minus infinity, which is like infinite value. It's undefined, no? You want the value to be finite, then only you can say that it is absolutely integrable. You are getting the value to be infinite, and hence e power j 4t is not absolutely integrable. Okay, very good. Right, now we have understood what are all absolutely integrable signals. There is one special signal which looks like absolutely integrable but not actually absolutely integrable. Okay, sinc of AT, sinc function, or you can also write or sampling of AT, this kind of function, sinc function or sampling function, or this also can be written as sine AT by pi t kind of function. Okay. These are three different forms of sinc function. We will play around with these functions in one of the future classes. So definitely, if they want to frame some interesting question, little tricky question on Fourier transform, uh, they'll be involving these sinc functions or sampling functions, we call them. Right. So we'll discuss about these functions in detail at a later part of the course. Right. So these signals, if you plot, you know how it looks like, right? If you plot sinc functions, you know how it looks like. It's maximum at one point, and they keep on decreasing on both sides, like this. The cycles will keep on decreasing its width. Sorry, width will be same. The height of the cycles will keep on decreasing. Signal will be like this. Sinc of AT. So sinc of AT means it's like sine pi AT divided by pi AT, something like this. Sampling of AT means it is sine AT by AT, something like this. So sine function, you know, right? It is cycles with equal positive and negative peaks, and in the denominator it is t. Observe this one. As t increases with time, the denominator increases. With time, the denominator is increasing, which means the cycles, one sine wave, whatever cycles are there, same cycles will be there. But since the denominator is increasing, the height of the cycles is reducing. Okay, at t equal to 5 seconds, sine takes a maximum of value of +1 and minimum value of -1. So sine takes values from -1 to +1. At t equal to 5 seconds, what happens? The amplitude of this one, it is sine, whatever cycle is sine wave is there, that same cycle will be there, but its amplitudes are reduced by 5 times at t equal to 5. Similarly, at t equal to 100, their amplitude is reduced by 100 times. Okay, so sinc function is like sine waveform whose peak amplitudes are reduced as t increases. Okay, so this kind of function, our common sense says that okay, the peaks, the cycles, amplitude of the cycles is reducing, right? Our common sense says that this might be absolutely integrable. For most of the signals, whatever our common sense says is correct. For most of the signals, by looking at the signal, we should be able to guess. We can guess actually. By with common sense, we can guess whether it is absolutely integrable or not for 99.9% of the signals. But this signal also seems to be, from common sense, it seems to be absolutely integrable, but this is not. This is a special signal. So if you want to verify, you have to apply this sinc of AT, one of these three signals. If you substitute and integrate, then you will understand this turns out to be infinity. The integration of this is not an easy job. It's very tough to integrate this signal. So if you're good with integrations, you can try it after the class. You can integrate this signal from -infinity to +infinity. It's not so easy integration, so that's why I'm not doing it here. But this value turns out to be infinity. So sinc function. If you write it in this format, we call it a sinc function. If you write it in this format, we call it a sampling function. But the meaning of both of them is same. The function which decreases both sides. Sinc function is not absolutely integrable. Sinc function is not absolutely integrable. This is a special case. Fine. Any doubts till this point? So this is one special case where the function looks like absolutely integrable from our common sense perspective, but actually speaking, this is not absolutely integrable. But for all the remaining signals, whatever our common sense says, by looking at it, our common sense will be saying correctly, except for this signal. Okay? Right. Any doubts if you have, you can ask me. Oh, you mean in sinc function? it's some constant. There is no significance for A actually. I've just written in a general format. Instead of saying sinc t, sinc of 2t, sinc of 3t, sinc of 4t, some constant can be there, no, here. So what I mean by A is some constant which is placed inside the sinc function. Generally we'll see, in mathematics we'll see it something like this, sinc x, which is sine pi x divided by pi x. This is the definition of sinc function. Similarly, one more definition is sampling function, sampling of x. The shape of both of them is similar. It is sine x by x. Okay, this is the basic sinc function definitions. So what I mean by A is some constant, sinc of 2t, sinc of 3t, sinc of 4t. So all with whatever constant you are talking about inside, for all constants our discussion is valid. Whatever constant you put inside the sampling function or sinc function, they are always not absolutely integrable. I'm just generalizing with that constant as A. Instead of putting some fixed constant, I'm just putting it as some A. Okay, right. Now I just want to revise something about energy signals. Energy signal, power signal, energy signal, power signal, and neither energy nor power signal. I'll quickly tell you some important interesting points about these signals, and I'll relate the absolute integrability condition with these signals, and I'll talk about Fourier transform existence for these signals also. There are signals can be classified in this manner, right? When you're talking about energy and power, so you can classify the signals as neither energy signal or power signal, or neither energy nor power signal. Every signal falls into one of these three categories. So we'll talk about when do we call a signal as one of these three signals, and what about the Fourier transform for these signals. So a lot of interesting discussion we are going to make here, right? So when do we call a signal as energy signal? If a signal has finite energy, if a signal has finite energy, signal can be called as energy signal. If any signal has finite energy, we can call it as energy signal, as simple as that. Or the condition is, you want the energy to be finite, right? How do we calculate the energy? Square the signal and find the area. That itself will give you the energy. This is how we find the energy of the signal. This is how we find the energy of the signal x of t. This is how we find the energy of the signal. And this energy we want it to be finite. For a signal to be energy, for a signal to be called as energy signal, its energy should be finite. Okay, right. So how to guess whether a signal is energy signal or not? Just by looking at it. How to guess if a signal is energy signal or not? I'll just tell you a point here. If a signal is finite in time, duration, and finite in time duration and finite in amplitude. This is how you can just look at the signal and guess whether it is energy or not. If a signal is finite in time duration and finite in amplitude, then signal is energy signal. By calculating energy, we can say that whether it is energy signal or not. Okay. Instead of calculating, just directly if you want to guess it, you can use this point. You can make use of this point to guess if a signal is energy signal or not. So let us try to guess. Okay. So we have seen some examples previously. Look at this one. Is this finite in time or not? Sorry, this is infinite in time, right? This is infinite in time. It should be finite in time and finite in amplitude. This is infinite in time but finite in amplitude. Correct? This is infinite in time but finite in amplitude. So can we say that this is energy signal? No, right? Because energy signal means what? It should be finite in time duration, which means it should have finite width, and its amplitude also should be finite. Then only we say that it is energy signal. Right? So this is not finite in time duration. So this is having infinite time duration. So this is not energy signal. Okay. Next, how about this signal? Is this finite in time? Yes, it is having almost zero width. So it is finite in time duration, and it is having infinite amplitude, right? It is impulse. Impulse is having infinite amplitude. No? If it is having infinite amplitude at one point of time also, that is fine. We can say it as infinite in amplitude signal. Okay, right. So this is finite in time, but it is not finite in amplitude. So this is also not an energy signal. Impulse is not an energy signal. Okay. Next one. How about this one? Is this having finite time duration or not? Yes, this is finite in time, and it is having finite amplitude also, right? At every point of time, it is having an amplitude of 100 or else zero amplitude. 0 is also finite, 100 is also finite. It is finite, having finite time duration and finite amplitude, and hence this is a signal which we can call it as, this is absolutely integrable, and also it is energy signal. Okay, how about the next one? This is infinite in time and infinite in amplitude. It is infinite in amplitude. So this is not an energy signal. Okay. How about the next one? This looks like, okay, this is a critical signal to analyze. So exponential signals, they are finite in amplitude. This is exponentially decreasing signal is finite in amplitude, correct? This is finite in amplitude, and it looks like infinite duration in time. Theoretically speaking, it is having infinite time duration, but practically speaking, how about that? See this one, instead of a, let us write it as e power minus 4t. Okay, at t equal to 1, what happens? It is e power minus 4. How much small value is e power minus 4? It's very, very small value, no? At t equal to 2 seconds, what happens? It is e power minus 8. Very, very small value. So within small amount of time, the signal is almost going to 0, right? Theoretically speaking, it has infinite duration, but practically speaking, it is having finite duration only, right? Theoretically speaking, it is having infinite duration, but practically speaking, it is having finite duration. So I'll say it as finite in time signal. When I'm saying finite in time or not, I'm talking about practical time width. Okay. So, and we have calculated the absolute value. This is absolutely integrable. And if you square this also, if you square this, what happens? It becomes e power minus 280. The result will be 1 by 2a, which is a finite value. So energy of this is also finite. We can calculate the energy and say that it is an energy signal. That is one way. Directly by looking at it, though it looks like it is having infinite time duration, but practically speaking, it is having a finite time duration, and hence we can say that it is a energy signal. We can say that it is a energy signal. Okay, fine. Next, this is not an energy signal. This is not an energy signal. This is not an energy signal. Because if area is infinity, can I say that energy is also infinity? Can we say that? Here area is infinity. Energy means what? Squared signals area only, no? If area itself is infinity, if you square it and find the area, then also it will be infinity, no? Just understand the relation between absolute integrability and energy signal relation. Are you able to understand the relation? A signal which is absolutely integrable has a finite area. Okay? A signal which has finite area should also have finite energy, right? Generally speaking. Correct or not? A signal which has finite area should also have finite energy, right? Correct? Right. So let me tell you the relation between energy signals and absolutely integrable signals. Generally, not always, not 100% of the times, but general cases, generally energy signals are absolutely integrable, or the reverse is also true. Absolutely integrable signals are also called as energy signals. There are only two examples which will not satisfy this condition. There are only two examples. So the examples also I've talked about. See this one? Sinc function is not absolutely integrable, but sinc function is an energy signal. This is an exception. Generally, almost all the signals which are all absolutely integrable are all energy signals. But this one is an exception. Sinc function is not absolutely integrable, but it is an energy signal. And one more example is also there, and that is impulse. Look at this one. Area of the impulse is finite. But since it is having infinite amplitude, its energy is infinite. Impulse is not an energy signal. Okay, but its area is finite. It is absolutely integrable, but not an energy signal. So that is another exception. Only two exceptions are there. And the other exception is, let me write the exception here. Other exception is impulse signal or function. Signal or function, anything is fine. Signal means particularly we talk about function of time. Impulse function is absolutely integrable. Impulse function is absolutely integrable, but not an energy signal. Observe this point. So these two are the things, these two functions, sinc function and impulse function, they are violating this rule. What rule? Energy signals are absolutely integrable, or absolutely integrable signals are energy signals. So apart from sinc function and impulse, for every other signal, without any confusion, you can say that if you know that it is absolutely integrable, or if you know that its area is finite, you can say that it is energy signal. Or if you know that it is energy signal, we can say that it is absolutely integrable. For all other signals, this holds good. Energy signals are absolutely integrable. Absolutely integrable signals are energy signals. Perfectly true. Except for these two signals. Only when they are dealing with these two signals, we have to be careful. Okay? Right. Now let me comment about the most important point that we should be commenting here, and that is I'll just put a star mark, okay? Sinc function is an exception. Impulse function is an exception. How are they an exception? I'm showing you, I'm writing a statement here. Okay? You can copy it quickly if you want. You can take a snapshot of it if you want. Is it okay? Fine. Now let me talk about the point that we should be talking about in today's class, and about energy signals. What about the Fourier transform of energy signals? Energy signals are generally absolutely integrable signals, right? Generally, all the energy signals are absolutely integrable, except one exception. Exceptions, let us remove them from our head. Let us remove them. But whenever, in particular, somebody is talking about exceptions, you can talk about them. But generally, energy signals means absolutely integrable. Absolutely integrable means energy signals. So if you're talking about energy signals, they are all absolutely integrable. And if for absolutely integrable signals, what can you comment about Fourier transform? Fourier transform of energy signals exists, right? Yes, generally all energy signals will have Fourier transform, exists and well defined. See this one, see the exception? Sinc function is not absolutely integrable, right? But still, it has a well-defined Fourier transform. Though this is an exception, though this is not absolutely integrable, which is the actual condition for a well-defined Fourier transform, but still, Sinc function has a well-defined Fourier transform because it's an exception. Okay, so what we can say is Fourier transform of all energy signals. Fourier transform for all energy signals exists and it is well-defined. Okay, right. Let us talk about power signals now. When do we say a signal is power signal? If a signal has finite power, if a signal has finite power, if a signal has finite power, then signal can be called as power signal. Can be called as power signal. Okay, right. So for energy signal, what can you comment about power of an energy signal? For energy signal, energy is finite. And what about the power? Power of the signal, power of energy signal should be 0. Why is it 0? I'll just tell you. Right. Let me write the formulas for energy and power so that you'll understand it better. Energy of a signal formula is given like this. Mod x of t whole square dt, limits from minus infinity to plus infinity. And basic understanding of power is equal to energy divided by time. Correct? So let me write it like this. Energy divided by time. But actual power formula, I'll write it like this. For signals, we write the power formula as limit t tends to infinity 1 by t minus t by 2 to plus t by 2 mod x of t whole square dt. So this is like, this part is like finding the energy, and 1 by t represents total time, energy divided by time. This part is energy, 1 by t represents divided by time. And what is the total duration of time in which the signal exists? Generally it is infinite time, right? So that's why in the limits we are not substituting infinity directly. What we are doing is we are substituting minus t by 2 and plus t by 2, and then we are dividing its total time, and at the end we are substituting t equal to infinity. Okay, just to remove the complications, we are doing it like that. But basically what is happening, it is like energy divided by time. And how much is the time? Time is infinite. Time is infinite. So observe this one. For energy signal, for energy signal, what should be happening? Energy should be finite, right? If you want energy to be finite, how should be power? Can you tell me? How should be power? If you want energy to be finite, how much should be the power? Or else, let us understand it like this. If energy is finite, finite divided by time is how much? Infinite. Finite divided by infinite, how much is that? Finite divided by infinite is 0 only, right? Is that okay or not? If energy is finite, finite value divided by time is generally infinite in signals, because we're talking about time duration, right? Time duration is generally infinite. Finite by infinite should be 0. So that's why, without any confusion, we can say that for all energy signals, energy is finite, but power is 0. But how about power signals? How about power signals? For power signals, power is finite. Power is finite. If you want power to be finite, see this one, this is finite. And how about energy? Send time on to the other side. Energy equal to power into time. Power is finite, into time is infinite. Finite into infinite is infinite only, right? So energy should be infinite for power signals. Because power is finite, into time will give you energy. Finite power into infinite time will give you infinite energy. Okay. Similarly, for neither energy nor power signals, what happens? For neither energy nor power signals, what happens is, it's like power is infinite and energy is also infinite. Energy is also infinite. Okay, right. So we've understood the relation between power and energy. Fine. Very good. So how do we recognize a power signal? So coming back to the discussion of power signal, we have defined what is power signal. For power signal, what should be happening? Power should be finite. Px of t should be finite, which means less than infinity, and energy of the signal definitely should be equal to infinity. For a power signal, energy is infinity, but power is finite. And how do you recognize a power signal? By looking at it, how do you recognize it? Very simple. If a signal is infinite in time duration, which means if a signal is having infinite time duration but finite in amplitude at any point of time it should be taking finite amplitude. It should never take infinite amplitude. Like impulse, r of t takes infinite amplitude at t equal to infinity. So nowhere it should take infinite amplitude. It should be taking only finite amplitude. If a signal is infinite in time duration and finite amplitude, then signal is power signal. This is how we can identify. And how about power signals? Are they absolutely integrable? Power signals are not absolutely integrable. Power signals are not absolutely integrable. Well, I'll show you some examples. Say this one. So this one, this is infinite in time duration but finite in amplitude. So this is the condition that I asked you to check for power signals. So this is not absolutely integrable, but this is power signal according to what we have defined. This is not power signal, this is not energy signal. So this will come under third classification, which is neither energy nor power signal. Next one. So there is no other power signals in this slide. So I'll show you one more. Right. How about sine and cos signal? Sine omega naught t, cos omega naught t. How about this signal? Is this infinite in time duration or not? It is having infinite time duration, and the amplitude, if you observe, for sine and cos signals, amplitude is finite. No? It is having finite amplitude. So cos and sine signals are power signals. Cos and sine signals are power signals. Not all periodic signals are power signals. Okay, cos and sine are power signals. But how about tan? Tan is not a power signal. Okay, you have to mind this. Tan is not a power signal. So tan goes like this. It goes to infinity, and then it will go like this, something like this. So tan is taking infinite amplitude, no? So if I'm talking about tan omega naught t, so it is infinite in time duration, and infinite in amplitude also. It is having infinite amplitudes, right? So that's why tan omega naught t. Don't think that all periodic signals are power signals. No. Some periodic signals are only power signals. Only periodic signals with finite amplitude are power signals. Not all periodic signals are power signals. Some periodic signals whose amplitude is finite, only they are power signals. Yes, tan will be the third classification. It cannot be energy because it is not finite in time and finite in amplitude, so it's not energy. So it's not finite in amplitude, so it's not power signal. So the third classification, it will be only come under the third classification, which is neither energy nor power. Okay, right. I've given you the examples now. So I'll tell you a little bit about Nathan energy nor power signals also, and then I'll comment about Fourier transform. Okay. So Nathan energy nor power signal. When do we say a signal is Nathan energy nor power signal? If a signal has infinite power, that is sufficient, no? Obviously, if power is finite, then itself energy is infinite. So if a power is infinite, then obviously energy also will be infinite, right? If a signal has infinite power, obviously we have infinite energy also. Then it is in neither energy nor power signal. Okay, and how do we recognize this? How do we recognize this? We recognize it if a signal has infinite amplitude at least one point of time, at least one time instant, at least one time instant or multiple time instants. If it is having infinite amplitude, we can call it as neither energy nor power signal. Okay, right. So that is the understanding of neither energy nor power signal. So let us go back to the examples. Now look at this one. You just need to check the amplitude. You don't need to check the time also. For neither energy nor power signals, you don't need to check the time duration also. See this one, it is having infinite amplitude at one point of time. So that's why it is neither energy nor power. So R of t is having infinite amplitude at t equal to infinity. At one point of time, it is having infinite amplitude. So this is also neither energy nor power signal, NENP. And how about this one? This is not having infinite amplitude at any point of time. So this is having infinite amplitude. So this is neither energy nor power. This is also neither energy nor power because at t equal to minus infinity, it is having infinite amplitude. And this is also neither energy nor power. And these two are also neither energy nor power because they are having infinite amplitude. No. So how about the last one? How about the last one? This is neither energy nor power, agreed, e power 3t. And because at t equal to infinity, it is becoming infinity. So it is having infinite amplitude at one point of time. But how about e power j4t? J4t is different from e power 4t. E power 4t is different from e power j4t. You have to mind this. E power j4t is like cos 4t plus j sin 4t. The magnitude of this signal is 1 only. This signal is never taking infinite amplitude. Correct or not? Even at t equal to infinity also, e power j infinity is different. E power infinity is different, e power j infinity is different. So this is what? This is having infinite time duration. This is infinite in time. This is having infinite time duration, but it is having finite amplitude. So what can you comment about this signal? What can you comment about this signal? It is having infinite time duration, but it is having only finite amplitude at any point of time. So we can say this is a power signal. Or we can also say it like this, right? E power j4t, we can write it as cos 4t plus j sin 4t. Cos 4t, cos signal is a power signal. Sine signal is also power signal. Sum of two power signals also should be a power signal. Right. So that way we can talk about power signals. Right. Look at this one. This is having infinite amplitude at one point of time. If a signal is having infinite amplitude at any point of time, we can call it as neither energy nor power signal. Right. So why am I talking about neither energy nor power signals? So actually this is like out of topic only, energy, power and neither energy nor power, but I'm giving you a little bit of clarity. The point I'm talking about these signals is I want to comment about whether Fourier transform exists for these signals or if it is not existing. So that is what I wanted to comment. So that's why I've given you a little bit of idea about energy and power signals. Basically, when I do a discussion about energy and power signals, it will be like a very long duration of class I'll be taking only for energy and power signals. It will take at least 3 to 4 hours. But anyway, I'm just giving you a brief idea of energy and power signals now. Right. So we've talked about an existence of Fourier transform for energy signals. Fourier transform exists and it is well defined. So same comment let us make it for power signals also. Let us make the same comment for power signals also. Inverse tan, yeah, inverse tan means it will be, limits will be only from minus pi by 2 to plus pi by 2. Sorry, minus pi to plus pi only, right? Sorry, inverse of tan will be minus pi by 2 to plus pi by 2. Yes, it will take a finite amplitude only. So definitely it should be power signal. Yes, inverse tan should be power signal. Right. So let us make the important comment here, and that is about power signals. Fourier transform of power signals. Fourier transform of power signals exists or not? It exists. But power signals are not absolutely integrable. You have to mind this. Power signals are not absolutely integrable. You have to mind this. But still, Fourier transform will exist. But because they are not absolutely integrable, what happens? Let us go back to the actual condition. See this one. If the signal is not absolutely integrable, what happens? Fourier transform will not be finite always, which means Fourier transform might take some undefined values. Fourier transform might take some undefined values, or Fourier transform might consist of impulses. Impulses there means what? At the location of the impulse, you are having an infinite value, right? So the Fourier transform might consist of impulses or some undefined values whenever you are talking about power signals. Because power signals are not absolutely integrable, since they are not satisfying this condition, Fourier transform might consist of a few impulses or few undefined values. Not many, but very few. One or two undefined values will be there. I'll show you some examples, then it will be more clear to understand. Fourier transform of power signals exists but not well defined. But not well defined. For energy signals, it exists and it is well defined. I hope you're understanding what I mean by not well defined. Not well defined because there will be some values at some locations, at some frequencies, the amplitude will be infinite. Simple example I'll give you. Okay, so from your memory you can just recollect what is the Fourier transform of u of t. If you remember Fourier transform of u of t, I have not derived the Fourier transform, but you might be having some idea, right? Pi into del of omega plus 1 by j omega. At omega equal to 0, what is the amplitude? At omega equal to 0, there is an impulse, which means at omega equal to 0, the amplitude is infinite. So at omega equal to 0, Fourier transform is not well defined. No, it's not well defined because it is undefined. Not well defined because it is the value of the signal at omega equal to 0 is infinity. Infinity is the undefined value. Since there is a presence of undefined values, that's why we are calling it as not well defined. Similarly, you can think of a Fourier transform of cos and sine signals. Cos signal, pi into del of omega minus omega naught, impulse is there. Impulse means undefined value is present. So some undefined values will be present. Okay. Similarly, let us make the comment for last signal also, neither energy nor power signal. So without any confusion, we can comment about this signal. Fourier transform does not exist for neither energy nor power signal. You don't need to think about it. It does not exist. It does not exist. Right? Wonderful. So for neither energy nor power signals, don't even think about Fourier transform. But for power signals, yes, we can think of Fourier transform. We can find the Fourier transform, but the Fourier transform will turn out to be not a well-defined Fourier transform. Right? For energy signals, Fourier transform exists and it is well-defined because you'll not be finding any infinite values or impulses in the Fourier transform of energy signals. I'll tell you one more point here. And Fourier transform for energy signals, Fourier transform can be found using Fourier transform formula. You may say that, sorry, is this a big point? Yes, it is a good point. It is a very good point. Fourier transform can be found by using the Fourier transform formula itself. How else we can find the Fourier transform? You may say that, yes. When I say the next point, then you'll understand what I mean by this. Fourier transform can be found by using Fourier transform formula itself. You know the Fourier transform formula? Only for energy signals you can apply the Fourier transform formula. For power signals you cannot do that. But then how can we find it? Yes, we can find it in alternative procedures. For power signals, Fourier transform exists, but it is not well defined. And if you want to find the Fourier transform of power signals, you have to use alternate procedures. Fourier transform can be found using alternative procedures, not by using direct formula. Direct Fourier transform formula cannot be applied for power signals. So if you want to find the Fourier transform of u of t, since it is power signal, you cannot apply integration of x of t into e power minus j omega t dt formula. You cannot apply that because this is power signal. But then sir, how do we find the Fourier transform? Yes, we are having alternative procedures. What do you mean by alternative procedures? They are not like a different. There is a different procedures for this. It's not like that. We're having properties for Fourier transform, right? Using one of the properties, if you are trying to get the Fourier transform, that is what I mean by alternative procedures. In further classes, tomorrow and day after tomorrow class, I'll get the Fourier transform of these power signals using some properties, duality property, linearity property, some properties. Then you'll understand what I mean by this alternative procedure. But one thing is clear. If you want to find the Fourier transform power signal, you should never use the Fourier transform formula. You have to use properties to get it. Can be found using alternative procedures, not by using Fourier transform formula. See, for all power signals, Fourier transform is not well defined. Okay, for all for all power signals, Fourier transform is not well defined. If you are having any confusion or any particular signal, you can ask me. I'll show you that it is not well defined. All power signals have a not well defined Fourier transform. Okay, for all power signals, you have to go with alternative procedures only. Okay. Right. I'll show you. So how we are going to find the Fourier transform of power signals by using a limiting case of energy signals. I'll show you that in tomorrow's class. Okay. If I talk more about it, you'll get confused now. So tomorrow when I derive the formulas for power signals, then you'll understand it better. Okay. Wonderful. So we have talked about Fourier transform, about energy, power signals, and neither energy nor power signals. How about the Fourier transform and how we can find it? All those things we have talked about for all three different types of signals that we know. Right? I hope it is clear till this point. So shall we stop at this place? In tomorrow's class, I'll start talking about properties of Fourier transform. Okay. So tomorrow it's a 2-hour duration. Tomorrow also it will be 2-hour duration class. Tomorrow and day after tomorrow. So we'll be solving questions also based on the properties that we will be discussing. So they're going to be interesting classes. So I'm going to complete the Fourier transform from end to end. So I'll try to complete almost everything, each and everything possible in Fourier transform. But it is going to take a lot of time because it's a big topic. There is a large scope for asking questions, and a variety of concepts are present in this topic. And it's a beautiful topic, but it is a very vast topic. Fine then. So tomorrow's class is on Unacademy platform. I hope I've told you that already. I'm again repeating, but tomorrow class is at 8 o'clock only. So tomorrow class is from 8 p.m. to 10 p.m. not 9 p.m. to not from 9 p.m. It is from 8 p.m. only. So tomorrow timing is 8 o'clock to 10 o'clock in the evening. Right. So we'll stop at this place then. We'll continue in tomorrow's class. If you're having anything to ask, you can ask. So for the sake of new students, let me give some idea about subscription part. So if any student wants to learn the complete subject of signals and systems or communication systems from me, so you're having an opportunity to learn it from Unacademy platform. So But if you want to learn the complete subject, you have to take subscription. And if you take subscription, you'll be able to attend all the courses that I've taken in the past and in the present and in the future. You can attend all those courses. So, and if you want to attend only the free classes, you can follow me on Unacademy page. So you can attend all the free classes of mine. You'll get the messages whenever I take a free class. And whenever I take a regular course also, you'll be getting the message. So if you want to attend the full course, you have to take subscription. Right. So once you take subscription, you can attend my classes along with all the teachers that are available on the platform, their classes also. So see, there are amazing teachers available on the platform. So you can attend the class of all these teachers. So there are multiple batches catering to the needs of different students, different type of students. So students who are targeting for GATE 2022, for them a separate batch. And there is a batch for students who are in the third or fourth semester. So for them, in this batch we'll be covering the semester subjects. And so this is an accelerate batch, which is meant for students who are attempting GATE 2021. And since there is not much time, so we are doing it in a fast track courses. So which means we are doing it, we're trying to complete the syllabus in a fast track manner by taking more number of hours per day, maybe 6 to 7 hours of classes you have to listen. So because only 4 months time is left, right? So for those students, we are starting a batch. So batch has started on 17th August. Second batch is starting from 31st August, I guess. So second batch B is also starting, which is at the end of this month. Maybe in another 3 or 4 days it will start. So if you want, you can take, you can attend any of the batches. There is no restriction on which batch to attend. So subscription is not for a particular batch. So subscription is for Unacademy GATE category. So once you take the subscription, you will be able to attend any batch, anytime, any number of times. You don't need to take permission from anybody. You can attend any batch, any teacher, whichever way you want. So, and there will be multiple options for every subject. So for example, so I teach signals and systems. There are two other teachers who can teach signals and systems. Similarly, I teach communications. There will be some other teachers also who will teach communication system. So like that, for every subject, there will be multiple options for you. So you can attend all those classes at the same with the same subscription. And coming to the subscription, the fees for subscription is very nominal. The fees is just 25,000 for 12 months of subscription. And you don't need to take a 12-month subscription if you don't want. So you can take subscription for a lesser number of months also, and the fees also gets reduced. Okay, so based on your requirement, take the subscription accordingly. If you are in need of complete preparation, it's better to take 12-month subscription. And if you are in need of a partial, maybe half of the subject's preparation, then you can take 6-month subscription. Or if you just want to try out the platform for a few days, then you can take a 1-month subscription and see how the platform works. And if you're impressed with that, then you can extend your subscription. Okay, and if you're a college going student, it is better to take 24-month subscription. As the number of months increases, the fees increase is very less. You can observe that. And you can note down this code. This is my referral code, we call it. So you can note down this code and you can apply it while taking subscription, so that you'll get some extra discount. You can note down this code. If you're taking subscription at any future point of time, you can make use of this referral code. Right. So coming to the last and important part. So this is my Telegram ID, personal Telegram ID. You can contact me on this ID if you wish to ask me any questions on anything that you feel like I can clear your doubt. So you can ask me on this personal ID. But if you're having any subject questions, maybe on signals and systems or communication systems, I'm running a separate group on Telegram. The name of the group is Signals and Communications, but you can search with this ID to get the group. You can add yourself to the group. If you're having any doubts in those two subjects, you can post it in that group. We can help you with the doubts. Okay, fine then. So thank you. Have a very, very good night. We'll meet again tomorrow at 8 p.m.